There we go.
All right, nice. So hello, everybody. Today we're going to be taking a look at the second of the Starks talks that Ellie gave at the Technion summer school. So the first part was it was a high-level review of Starks, and this one was getting into the topic of low-degree testing. Additionally, there is a paper that is the basis of this talk, which is the Fry paper, which unpacked is the fast Reed-Solomon interactive oracle proofs of proximity. I also linked to this paper inside of our Google Doc notes for each session. And so this was kind of the meat of this talk. So the overview was split into three parts. So what is the Reed-Solomon proximity problem, which is effectively the low degree proximity testing. And then he went deeper into what is the Fry protocol that they made. And then it ended in a very, very in-depth look at, or tried to make the comparison of fast Fourier transforms and how it's similar to Fry, basically in the recursive nature and how you're going to split the problem into some subproblems. So the format that we're going to be doing is 10 minutes of introduction by me, who's leading the session. And then we'll ask everybody who's on the call for questions that they have, either related directly to this presentation or some ideas that get sparked as we're talking about it. And then we'll have about 40 minutes of discussion. All right, so for me, when I was watching this presentation, I think the things that stood out again were something similar from the first talk, which is when you're saying that you're assuming a function f, to think of it also as a lookup table. This helps me kind of better reason about what is happening here. So just that you have an f that's taking an input, and if you were to have that input, let's say it's x, you could just build that lookup table. And this is very useful in practice because you could have pre-computed this lookup table. So again, the overall problem statement is that you have f and it's in it's in some set S, and we're saying that S is something huge, so it could be billions. And as it turns out, this is really important for the work that Eli had done in another of his theorems in 2005, that only until the set is very large do you start getting the cost benefit. And so I guess this is why they wanted to come back and take a look at Fry, so that you could lower the number of queries in order to construct the proof. So kind of going through this. So it was, I guess he made a note about saying that the previous talk, the Starks 1 talk, was about using low degree polynomials to express the statements of computation. And here he wanted to, or here what he's talking about is not really talking about the computation at all, but just breaking it out into the algebraic form, which again for me was realizing that, okay, I don't have such an intuition as I'm looking at the notes and the formulas that he's writing on the screen. And I found that there was a lot of gems listening to the way that he described this. So for me, my notes are half of what he has on the slides and more about what he talked about and how he kind of unpacked it, so I could better understand how different parts of the formula are talking to each other. So at least for me, that was really important. So really watch the talk and don't just read the slides, because he explains it in a great way. Just again, adding slackness is kind of the important part. So the problem statement truly is that if you were to have this 0.1 far, so if you're allowed to have 10% of all the entries in F to be off, but not more than 10%, can you still have an efficient way to query into F? And so we have the first step where we're saying let's simplify it, and then to further simplify it, we're saying that we want to have an error of half still with this minimal q. And so specifically what that means is that when f is this low degree polynomial, Alice must accept f if it's an honest polynomial, And if f is very far from being low degree polynomial, then she must reject it with the probability of half of this 10%. And so really, this is the simplification, the slackness that allows, I guess, the underlying math to all line up. And so breaking it down, starting with just a simple polynomial, which is a line. So when you have these 2 points, if you want to reject any lookup table that's not close to representing that line, so that means you need to change more than 10% of the entries. How would you do that? Well, you can say that we'll find the slope and the intersection of the line by reading 2 points. So for a line, you can just read 3 points, and so for the first 2 points, find the slope and the intersect, and then take the next 2 points and see if it is matching. So then for any polynomial, as you're increasing the degree, you're going to need at least degree many points, so degree many queries to interpolate that polynomial. So the first theorem that he talks about is this work that was done in '95. I forget the person's name, but the theorem is stating that you can do this with exactly degree plus 1 points. So when we had the example that we want to query, that we want to have this degree of g that is 1,000, you can query with 1,000 plus 1 queries. However, this is not with a proof, so we can't trust this yet. And so he continues, to solve this. And the important part the important note, I thought, was that we are in a transparent system. So for the proof pi that Bob makes, he writes down the f and the pi and commits to them. And so you can commit to this using a Merkle tree. And then later on, he's going to open up some entries. And so I guess it's, kind of by side, not so important, but by side, there's no cryptography in all this low degree testing or even in the Starks 1 talk. Cryptography is only being used to enforce the commitments and later on when you're revealing, so that the revealed entries are agreeing with what was committed to. And he called this transparent land. I don't know if anybody else has said it this way, but it was interesting to note what parts of it are just completely the mathematics, and then when do you start adding proofs? Which, I mean, for me, it wasn't such a surprise that it's only about committing and revealing. This is where you're going to have these these cryptographic assumptions, and when you start needing to use cryptography. So that was the introduction to low degree testing, and then he goes a little bit deeper into what Fry actually is. And so concretely, for the problem that we had, where we're in a set of 1 billion, and we have a degree g, which is 1,000. Concretely, we plug in some numbers, and it turns out that the prover complexity is concretely large at 27,000 queries. So it versus the previous theorem, which would have been 1,000 plus 1. So this is great because it's asymptotic result, because we have this log to the c inside. However, they're only kicking in when you have a very large, when we have a very large value. He shows another example later on where it's actually more expensive. You need more queries using this Fry setup. So this is something, I guess, to keep in mind, that if you don't have a very large execution trace, then using this is going to be more expensive. But I'd imagine that most of the time it is a large execution trace that we're working on, and so this is why you would do such a thing to begin with. So then he digs a little bit deeper to what Fry protocol is. Maybe people have specific questions that we could get into later. Otherwise, it was a lot of breaking it down, and the tricks that he used made sense, exactly in the part. So we could just come to the part where we say, when we have an f, which is some set f, and the function little f, and it's a set in the field f. And again, we're saying that we have 1 billion and the degree is 1,000. Then the previous work was that, okay, you have 1,000 plus 1 or 27,000 queries, but you have a proof. And with this Fry protocol, you're going to have query 80. because you're going to have 20 queries to get this soundness for error of 10%. And then you're repeating this 4 times more so that the soundness is no more than half of this farness, so this 10% farness. So this was, this was interesting. I don't know why, or if there is a generality to be made here about why it's 4 times more to get this error reduction of half. And additionally, he was saying that future work, there's not much left to save in the prover and the verifier complexity, but possibly there's something that could be done for the number of rounds. I missed it. I think it was the number of rounds of querying. And additionally, he made a side note that I wish we could make fast Fourier transform even faster. He gave no hints as to if he stumbled upon something or just that it was a wish of him. And additionally, this is an interactive protocol, so he made mention that you could apply the Fiat-Shamir heuristic to remove the interactiveness and make it non-interactive. And then for those that are really interested, he made he walked through and broke down what is fast Fourier transform, what is the inverse, and kind of mathematical statements about what these are doing. And then trying to show how Fry is similar. And I ended up writing a lot of notes here. It took me a while to unpack it. I still didn't quite follow all of it. So I think this is where I might start leaning more into doing things with pen and paper instead of just taking notes. Yeah, I ended it with ... more to come. So I will finish taking notes for that section of the talk. It's really just the last 3 minutes that's missing. But I guess the one weird trick to make this all work and why it's quite fast is that you are splitting the problem domain. So for fast Fourier transform, you are mathematically splitting it into 2 subproblems, and then continuing to iterate until you end up with a constant value that you're trying to solve, and then roll back up. And he's saying that it's something similar in Fry, except instead of splitting the subproblem into 2, or instead of splitting the current problem into 2 subproblems, you're getting a reduction of half, but kind of only following along one branch. You don't have 2 new things to solve. You're just still solving the same one. Yeah, so this was my overview of things that stood out for me. So now to turn it to the group and say, what were you thinking of, or what open questions do you have? And then we can start a discussion on that.
Okay, cool, thank you. I didn't get to the end. Like the part you just described, that's where I was like, yeah, and then we started doing the setup. So this is good to hear. But it sounds like I'm maybe, even after this, I might watch it and like watch it multiple times. I think we wanted to use the next like 5 minutes, or not even, but just to see if there are some like larger themes, questions that we could cover. So I don't know if you guys had specific points. I mean, I have some points, but these are possibly also just points that I didn't fully understand the kind of, like, for example, the 0.1 or 10% far, I actually didn't understand I didn't like fully get what that is, like what that meant, being out of range or something. So that in general, like I'd like to talk about. There was some talk of randomness, or there's this like pi, and I like, when you talked about it being transparent, I didn't understand how those were exactly related. I mean, I have some idea of how that might be related, but I wanted to dig into that a little bit more. And then I also agreed with you on the Forex. I don't know why that, like,
like the rudimentary math doesn't check out. If it's 1% at 20, it's 10% at 20, it's not 50% at 80. So
that's also one of yours then? The
yeah.
Okay.
But maybe I just misunderstood what he meant by 10%.
Yeah, I guess that covers most of the ones that I wanted to dig into.
Okay. Yeah, I'm capturing all these questions. That's why I'm muting, so you don't have to listen to me type.
Alistair, did you have anything?
Questions? No.
Did you understand?
Well, I have some questions, but not about the talk.
Okay. Do
So
you know how to explain, and maybe because you also had this, Christopher, that Forex question?
no, I'm not even sure where it came from.
Really? So like the idea, I mean, yeah, because it was sort of like you repeat it was it in rounds? Was that where the rounds were actually happening? So it's 4 times that round to be.
I was trying to do the math because it was like if you do it once, you get 10%. If you do it 4 times, to Chris's point, it's like if you do it 4 times, then is it like 0.1 times 0.1 times 0.1, or the probability of you being off being very small? But I also didn't get that part, and so the question is if no one gets it, then how do we solve it?
Well, what we are doing with these questions, that's actually a really good question. So like last time, because we have this group, and actually Ellie's in the group, what you can actually do is in this conversation, if we're not able to solve something between us, we will just drop it in there and hopefully either get his attention or somebody else's attention who can help us explain that or point us in the right direction. Last time, Alistair found an issue, or like you found something where we weren't able to figure it out, and so we just dropped it in the group.
Yeah, and that was very helpful. He gave an answer which also leads to some complications in describing this thing that he completely ignored in the talk. But never mind that, because that would only confuse people. So yeah, the 10% far here is what that means is that we disagree on more than 10% of points.
So is that sort of like a fuzziness, like they're wrong, or?
Yeah, we can't tell if we're exactly a low degree polynomial without checking almost every point.
But you're allowing for some, like, I'm just curious, is it sort of allowing for some error or allowing for, because I mean, I don't understand how that lowers the number of queries.
So if you want to hide that you're a low degree polynomial, that you're not a low degree polynomial, then the way you could do that is start with a low degree polynomial and then change 1 point. And there's no way that anyone's going to be able to detect that unless they have the actual polynomial. So, but if you change a lot of points, then there's a possibility that they're going to be at that. If they look at a random point, it's not going to be from this low degree polynomial.
So to visualize that,
yeah.
If I think of a line, right? I'm very simple, right? Think of a line. You add 1 point, you get a parabola. You add another point, that's not on the line, of course. Sorry for that. Then you start adding you're saying add a bunch of points. Basically, you're increasing the complexity of that polynomial by a degree every single time, probably, right?
Well, no. So so if you imagine having a line, we have a number of points where x is equal to y, and then you change a single point, so it's not on the line. So we have a line and then one outlier that's not on the line. And if we look at random points, we just can't find this 1 point.
Right. So I guess this is for me where it helps to think of this function f instead as a lookup table. So if we were trying to hide, if we were trying to hide points, then we could say we have this line, and so you technically have an infinite number of points, right, between an x and a y on a line, because you could keep making smaller values. So okay, great. And then you could pick a random point and put it in that lookup table. So as Alistair said, unless you look at everything that's in that lookup table f, that would be hidden, because if you have so many points inside, just changing 1 or 2 of them, the chance of you finding it is quite small. If that makes sense, because in this mental,
I still don't understand how that helps lower the number. Isn't like the purpose of this to lower the number of queries needed?
So I mean, we want to. It's kind of if this really was 10% far, there should be nothing the prover could say to the verifier to convince them that it's 10% far. But if we only change 1 point, then it makes the problem of hiding that we're not a low degree polynomial a lot easier for a malicious prover, and so it's very much more difficult for them to construct a proof that actually works.
Sure. So it seems like there should be some chance of, if the prover were lying, discovering the error on a random query to a random point as a function of the actual degree of the prover's polynomial versus 10 to the third, or whatever we expect to be open when far from. Is that right?
But there's only a chance of doing that if a random point will give us something useful.
I guess because it's the same, quote. I'm referring to my notes, so this is paraphrased directly from the talk, but it's the same game as what we were discussing from the previous talk, where when f is a low degree polynomial, there exists some pi, this proof that Bob is proving, and he's proving it over multiple rounds, right? Because that's where the randomness comes in. That the randomness that Alice, the verifier, is sending gets included in the next proof. So you have, a P1, P2, all the way up to a P of n for n number of rounds. So when f is a low degree polynomial, there exists some pi that should be accepted by the verifier. And when f is not low degree, then for any pi that Bob tries to fake, Alice should find out. So when I guess we get to drop the number of queries because a couple things. We've relaxed it, right? We're saying that even when we've done this 80 rounds of querying, we're still saying that there's a 5% error rate. So it could be that Bob is able to cheat, that the prover is able to lie. But you could continue to pump. It sounds like you can continue to increase the rounds. Again, this is what I'm wondering. I'm not sure what the ratio is there. 4 rounds more dropped it to half. So maybe that is, for some reason, if that is the math, then every time you do 4 more rounds, you're dividing it by 2. Is that it? Or is it actually a square there? Like you need to do 4 by 4. But yeah, I think that to me is my current understanding of the relationship to dropping the query number.
So yeah, I think here we actually need to use this thing from the last talk, this equality of polynomials, by looking at low degree polynomials, by looking at random points. We kind of need to do that here. Mm-hmm. And then in the end, we're reducing to testing if something is a line or something, or is a degree 1 or 2 polynomial.
Mm-hmm. Yeah, which once again, the power and beauty of recursive algorithms. But
yeah, but then in this base case, this is where we kind of definitely need this 10% far thing. If we're checking random points, it should be it's impossible to tell if we only change a few points away from a line or quadratic, we can't tell. Mm-hmm. But if we change 10% of points, if 10% points are away, then all we need to do is to look at 2 or 3 points to work out what the thing is, and then keep testing other points and say if they're still on it. And we don't need many points to get to random points to get something from this 10%.
Do you have any, or does anybody have any intuition why 10% far was the number described in this talk? I mean, each time Ellie is saying, I'm not going to go deep into the math, so till now I'm kind of trusting that the example he set up is somehow representative. But does anybody know why 10% far was chosen?
A good question.
All right, I'm gonna write that down for the future, because that was also Anna's other point. 10% far. What is this, and maybe why? Or if you were to concretely implement this for use case, why would you use 10%, or how do you pick that number? I feel that it's the end result is you're trying to choose an error rate which is acceptable.
Yeah, so I think looking at the paper, there was something where they don't quite know how to make this scale with the error in the way they'd like.
Okay.
So they probably do have to deal with a quite big number. like 10% as opposed to 0.1%.
Okay.
This could be totally wrong, but like thinking it from the perspective of a lookup table, if you want to find out if something is, you know, if you want to find your likelihood of, maybe again, this is just thinking up in my head. If you want to, the likelihood of you finding an error is sample this 10 times and you should find at least one error. I don't know if that's relevant at all whatsoever, but like thinking from a different perspective, again, this is.
That's exactly it.
Okay.
That's exactly it. But the reason, one of the reasons we're all wondering why you can sample it 4 times and get to a half, because that wouldn't make sense.
Yeah, no matter what you multiply, it's hard to get half out of this whole thing.
So that's what you said. Sample. Is it sample specific points, and one would be off?
Well, yeah. If you think of it as like Matt said, to look at it as like a lookup table, right? Don't think of it as like a continuous function. There's basically a table of all these points that someone puts up and says, "Hey, this is my polynomial." If someone tells you that there's a 10% error or 10% of those points are bad, you should only need to sample statistically 10 times, and one of those 10 samples should be wrong.
Well, you'd probably do more to actually get that, but yeah, I imagine, right? You wouldn't actually just do 10.
Well, statistically saying, right, you technically need to do just 10. It's like coin flips, right? You can do a bunch of coin flips, get heads in a row 50 times.
Right. Yeah, and this then, just to chain on to that, this leads into the other question you had, Anna, which is what is pi and how does that relate to randomness? So,
and also the other side of that is also, is there anything public, like this concept of transparent land? Was this that it's public randomness that's included?
Exactly. Well,
and
so
is pi like also pi? Maybe I'm just really not used to looking at math this much. But is the pi, is that just a symbol for anything, or is that like pi? That's not.
No, so it's pi. It's pi as a placeholder. So pi as a variable.
Okay.
And so the idea, I guess, the idea of transparent land, I don't know. That's a new word for me. But the idea there is that it is public randomness. So my
interpretation of that transparent was. In like, I think from what I recall, and I watched the video very quickly, apologies for that, is it was sort of in the context of like Zcash and the privacy preserving like stuff, right? Like that, hey, all of this stuff is actually happening out in the clear. No one's encrypting anything. No one's hiding anything right now. This is just sort of representation of knowledge, right? So that's how I interpreted that. I could be wrong, but in my head it was like, yeah, you want to sort of make it clear that, hey, this is like nothing to do with cryptography, nothing to do with anything, being able to hide something. It's really just about this fundamental concept.
Well, yeah, this is about there not being this toxic race, this crypto stuff. But of course, this is their knowledge. The prover might be hiding something.
Right. Yeah, and so this is it. Mathematically, we're trying to reduce the amount of stuff, or reduce at all if you try to drive that error rate to a very, very small number. You're trying to reduce the amount of times and also the amount of points that the prover could lie about. But so for all this public stuff, like anytime you hear coin flips, it's essentially saying you could have taken a value from like a public random beacon, as it's getting talked about in some of these implementations. Additionally, it was mentioned you could be using a block hash, right? That's also a public source of randomness. You don't know what a block hash is going to be until it's there. So this is why it's
I don't know if that's quite right. I think that's only true if the prover is never like the miner of a block, right? I think they're sort of simplifying the assumption there.
Yeah, so agreed. There's, there be
ignoring shady miners.
Right.
Yeah.
Right. Because the prover can't know. If the prover knows the randomness, they can cheat. It's not public in that sense. So.
But I guess what you're saying here is you can sort of you're lumping this together with those kinds of ideas of the random beacons, or using block headers, or just introducing randomness in order to make it more and more difficult to be.
Yeah, and I guess at least for me, when I'm thinking about this, having a good source of randomness is hard, and probably having a public source of randomness is also saying somebody could go back and check that you weren't having a bad seed to whatever random function you were using. So Alice, the verifier, wasn't also doing something weird, right, or something nasty. And then that public source of randomness is getting fed into the next round of pi, which is this proof of proximity. And so this is the auxiliary data that Bob is including and, until you do n number of rounds. And then at that point, that's also going to be committed.
Right. So first thing is I'd love to give lead the session where we start talking about the Shamir heuristic.
Yeah.
Because so that this is how we have this thing where the verifier has randomness, but we want to make it non-interactive.
Oh, yeah.
Then, of course, the prover has to come up with the randomness themselves.
Oh.
But yeah, later.
Cool.
Also, Link, I have not yet read it and so cannot summarize it, but Vitalik has a blog post on Fry, although it's called something else, that seems to summarize what pi is and why adding that auxiliary data reduces the number of queries required. I'll try to read it in the next 5 minutes, maybe.
Yeah, don't rush it, but if you want to, you could drop a link in the Telegram channel.
Yeah,
that'd be great.
Great.
I have a quick logistical question. Is it possible to join this now? Because my computer's about to die. I want to join from my phone.
I think you can keep joining. I think it's open.
I got a weird error that didn't let me. So don't worry about it.
We are going to put this on YouTube later, so you can also just watch it.
Okay.
Okay.
Okay. So Forex is still a question. Making it interactive is super interesting, and I'd love to just go more into that because that could be a bigger topic.
Sorry, I didn't catch the.
Interactive. Wait.
Yeah, Luis.
What are we doing to this?
Making it non-interactive.
Non-interactive.
It is interactive, and we don't like interactive because interactive plus blockchain doesn't work. So
right, yeah, but this is a topic for
written right in front of me. It is interactive. I should have known that.
This is a topic of a later talk, almost certainly. Yeah.
So I don't. Yeah. Can you hear me?
Yes.
Yeah.
No, I didn't understand the question about the non-interactiveness and what is the problem about it.
So the problem is that the prover has to come up with the randomness to verify something they
themselves. Yes, that's what the Shamir, the Fiat Shamir does. Yeah.
Exactly. Yeah.
That's if
that's what the Fiat Shamir heuristic.
Or right now the prover needs to also come up with randomness.
Yeah, right. That's always the case every time you have an interactive system.
But for the interactive version, which is what we're at the moment, but this is why the verifier is only allowed to give random numbers.
Right.
Because we're eventually planning to have the prover do all the random numbers.
Sorry.
Okay. That was all the questions that we had come up with.
So far.
We said I had written down. If I missed something or if something else has popped up, let's kick it off.
I think I've definitely covered most of the stuff. Oh, actually, I had a question about. I have an idea of what the answer is, but prover complexity was 27,000, and I thought. I guess like when he says prover complexity, that's a good thing. I guess the high number is good given the low number of queries, but I didn't really get why that was sort of like yay.
The prover complexity is bad if it's big.
Oh, it's bad.
It's bad if it's big. Yes.
So you don't want it to be big.
You don't want it to be big.
So then that's very confusing to me.
Well, so the way I think about that one, and here's how I rationalize that is, if it's going to take a lot of work to prove this thing, then if you try to run this on a blockchain, then it's going to be a lot of gas in the contract to prove that it was right. Is that right or wrong?
That's what I thought when I saw it. But at the same time, it was sort of like Wasn't that shown at the end, kind of like achieved prover complexity?
Yeah. So this is it's bad if it's large, but 27,000 is much smaller than it might have been.
Okay.
And additionally, I mean,
yeah.
probably the prover complexity is always going to be off chain at least. So really having the verifier, like the verifying complexity should be quite low. Otherwise, it's not going to be suitable at all. But
yeah,
definitely this off chain work should be small as well.
But so the thing we're doing, the degree, this 1,000, whatever so for instance, the degree before was the length of the execution trace. So it's got to be at least 1,000 for the prover. The fact that it's only 27,000 is great. It's much better than 1,000,000.
Oh.
And I think there are zero knowledge things where at least one of the systems I remember the prover complexity was quadratic in the length.
Mm-hmm.
So that would be millions.
Mm-hmm.
So 27,000 is great.
But this is not 27,000 is not the number of queries. Queries in this case were 80.
No, this is how much computing time the prover takes.
Oh, I see. Okay.
So the prover, the prover needs to do some work.
This is to produce pi, right? That's what we're talking about.
Is it only pi, or is it also about setting up the f? Because there's something to be done there about finding a polynomial for the thing that the prover wants to make a proof of. Or so that's a good question. I'm not sure if it's only.
It seems like this was sort of an independent construction, like for any such f that they already have.
Good question.
Like at least the prover complexity note comes much further after that section, so I don't know.
I'm looking through my notes because 27,000 comes up twice. Once Anna, it does come up as the number of queries, and so this was the work that was done previously by Ellie, and this is where it went from 27,000 down to 80 in this FRI protocol. Okay. And then the second time it comes up is when he's saying concretely with FRI, when you have this log to the C and we're using 1 billion as the execution trace size, as a set size, then that number is exactly 27,000 also. But I think that's just coincidence. Right. There was. So I guess anecdotally, there was one other part that was exciting for me, which is when he was talking about the properties of Fry, that he was, as he breaks it down, you end up with this T sub P, which is the number of arithmetic operations that the prover is making. And he was saying that some of them are additions, not just having a multiplication cost. And additionally, that this T sub P was parallelizable. So you're getting logarithmic time, and you can, hardware accelerate it to split it up. So that for me was really interesting, or exciting rather, because anytime you can chop it up, definitely hardware keeps getting better, faster, stronger, and so this is nice.
Wasn't there also a comparison there though, where it said I think it was the IFFT was parallelizable? Like, remember he was saying like you don't have to because you can, or at least. So I didn't actually watch the end of the video, so I didn't actually see it. I was just following your notes on that part. But where you said like it's actually faster because you're only doing one branch.
I mean, he did make us. I mean, it was apples and oranges as he said it. That he was trying to show that FRI is similar to fast Fourier transform because of the algorithm and because you're recursively going to a subproblem. If that's what you had in mind.
Kind of. I think I need to watch that part. Might have just.
Okay. Yes.
I think you're back, eh? Hi. I think. Oh, we can't hear you though.
Okay. So then, yeah. Last call for open questions or any other thoughts you had for today's session. Otherwise, Anna, you wanna close us out?
Oh yeah. Okay. So I think I would say we spent probably like more time than I will try to in the future on the beginning, getting it set up and stuff like that. But I really liked your overview. I'm now kind of annoyed that I didn't watch that last part because like it's kind of interesting and I can't talk about it. There's some points that I can tell I'm gonna have to like go over a few times before they fully sink in, but it was cool. I don't know. I thought this was a good session. I think this was like, for you, Alistair, maybe it's not super deep, but for me at least, and maybe for some of you guys, I think it was like pretty cool to see some of the like inner workings and some of the math behind it. And I'd love to do more of these. Yeah, I don't know if I need to say anything else. We're going to be doing another session next week. I think we're going to have a guest lead. We're going to talk about it in the next few days. And like I said, if you guys want to do one, Alistair, if you want to do one on Shamir heuristics, that would be awesome. Christopher, if you want to do one, let me know. And yeah.
Yeah, would, I guess, the three people who are on this call still find a discussion of how to construct simple Sigma protocol zero knowledge proofs interesting?
Mm-hmm.
Sure.
Like into deep into the math. So that's what I want to understand. Yeah.
I'd also like, I mean, so I was in a trusted setup workshop and it was really cool, but I'd love to do more on that because I was just watching and it was like there was a lot of stuff I couldn't do too. So
like the multi-party compute part, or just about the trusted setup?
It was actually
about the ceremony or the requirement for toxic waste?
It was the ceremony, and there were some kinds of, I think it's very much like in I don't know that it was going past what Zcash did, but it was kind of like replicating. It was like the planning of a ceremony of Tao.
We could do one better than that. We could do a ceremony.
We could, but like there was a few points to that I just like, I can't remember off the top of my head. It was like damn it. Wait, actually, maybe I wrote it down in here. I think it was, just one second, bilinear pairing. And yeah, no, I think that was the one. And I was talking to Rob Habermeyer about that, and he was like, "Oh yeah, that's like complicated." So that was a part where I just like think going through the steps might be interesting in a little bit more depth there.
Is it? Yeah.
That could be cool to do a ceremony. I guess something else that's been kicking around in my mind was how to go deeper into the math. I think I would be very excited to have Alistair lead us through Fiat Shamir heuristic and how that gets constructed.
They have another paper on how their specific thing works, which I'll have to look into. I don't know if there's a talk anywhere. That's what we need to find.
Right. Yeah. I mean, I guess I'm
actually, it doesn't have to be a talk. It's just like, but it like ideally one piece of content that could be read or watched or what have you in like half a day. So like not a whole course. I think we're not ready for that for this. I think the idea here is like we have a group of people who often are working and they have like other things going on, but we want to see if they can take some time to like look at a piece of material and then come talk. So.
Yeah. So I guess for me, the interesting part would be, or the unknown part is, if we do something that's very mathematically heavy, what do we do? Do we have the video, the video running and make sure that you're in a room with a whiteboard so you can lead everybody through? Because I guess this is the challenging part about having us on a Hangouts call, is how to walk through an example of it.
Well, there are some other tools that we can definitely look at. There are some tools where you can like do combo joint, like drawing on whiteboards. And we could do a screen share on that maybe. But I think for now, maybe we keep it to piece of content note. But yeah, cool. I think I'm ready to stop it.
Yeah. Thanks everybody for joining today.
Yeah, thanks a lot.
Thanks for presenting.
See you guys soon.